So heat transfer through natural convection, and here we are going to determine the surface heat transfer coefficient for a vertical tube, and this is losing heat by natural convection. So here we are having a brass tube, and there are about 7 thermocouples this fitted on the surface of this brass tube, and one thermocouple it's for measuring the ambient temperature. Now we are keeping this brass tube in a rectangular frame because to avoid the external disturbance, and there are opening on the top side and down side. And now what we do is here, if we are having the surface temperature of that brass tube, and if you are having the ambient temperature, then look, this heat transfer coefficient is equal to Q by area of surface area AS into TS minus TA. This AS means here we are having a brass tube, and inside this brass tube a heating coil is kept, and 7 thermocouples are kept on the surface of this brass tube, and we are supplying heat energy to this coil, and if we are having knowing the voltage and current, we can find Q is equal to V into I. Then surface area of the coil AS, surface area of the brass tube, that is pi into D into L, where D is the diameter of this brass tube and L is the length of this brass tube, which can be obtained from the specification of this brass tube. So diameter is 38 mm and length is 500 mm. So now Q is V into I. So if we are able to obtain that V, I and temperature, we can find heat transfer coefficient. So first we will be switching on this main switch, and then MCB, then the panel switch. Okay, initially this dimmer stat should be at 0. And then what we do is inside this coil is having about it's having a capacity to hold about 100 watt. So we are maintaining the heat supplied inside that 100 watt by adjusting the voltage. So let's keep that voltage at say 80 volt. So okay, it's 79 and the current is about 0.35. That means the power supplied is about 24 watt. That's okay. It's under safe condition. So now here we are having the readings of thermocouple. This knob shows the thermocouples, 8 thermocouples, of which 1 to 7 represent the thermocouples on the surface of the brass tube, and the 8th thermocouple represent the ambient condition. So what we do is we are having a column like this, T1 to T7, and then T8. T8 is the ambient condition. That's will be same. So we'll be taking the reading initially T1. So T1 is 32 degree, then T2, T3, like that we will be taking the reading. So now we have T1 32, T2 32, T3 32, now T4 again 32, T5, like that we will be taking the reading. So after taking the first set of reading, we will be taking the next set after 10 minutes. So we will be taking readings after the interval of 10 minutes, and at last a state will come when suppose say now the reading is 31, 31, like that, 38, etc., 33, etc., and at last a stage will come when the readings of that particular set will be same as that of the previous set. That means now it have reached a steady state condition, and at that time we can take the average of first 7 thermocouples, that is T1 to T7, and we can find the surface temperature, and the ambient temperature will be obtained by the reading of the 8th thermocouple. And then so here what happens is, from inside the coil heat will be emanating to the surface by convection, and so what happens is, because of this heat, the density of the air will be decreasing, so air will rise up, and because of rising of air, more air will be pushed towards the lower side from the lower side, and because of that this air will be carrying heat outside, and natural convection occurs. That's what happens here. So we are able to obtain Ts, Ta, and Q is V into I, As is pi dl. So now we are able to obtain the heat transfer coefficient. And now HL by K is equal to 0.59 into Greshoff's number into Prandtl's number is to 0.25 if GRPR is in between 10 raised to 4 and 10 raised to 9, and it is equal to 0.13 into GRPR into 1 by 3 if it is between 10 raised to 9 and 10 raised to 12. So what we do is we are having the Greshoff's number GL cube beta delta T by mu square, where beta it is 1 by TF plus 273 and TF is equal to TS plus TA by 2. So now from that we have beta. G it is acceleration due to gravity, L is the length of tube, and delta T is TS minus TA, and mu it is the kinematic viscosity of the AM. So we are able to substitute these values and we are getting the Greshoff's number. Similarly, Prandtl's number is Cp mu by K. K is the conductivity, mu dynamic viscosity, and Cp is the constant, this heat constant. Cp, that is heat constant at a constant pressure. So here from that we are able to obtain this Prandtl's number. So GR into P, we should find GR into PR. Suppose say it is about some 10 raised to 7. Then what we do is we'll be using this correlation, and from this correlation we will find H, and we will relate that to the experimentally obtained H, and then we will get the which one we will get the we can relate whether the obtained value is correct or no. That's about heat transfer through natural convection. Thank you.